For centuries, there was one dream that simply would not die: turn lead into gold. Take one element, one kind of stuff, with its own weight and its own stubborn character, and change it bodily into another kind entirely. The alchemists chased it for whole lifetimes, hunched over their fires in cellars and back rooms, mixing and heating and muttering, and every last one of them failed. And so eventually we did the sensible, grown-up thing. We filed the whole idea away under fantasy. Fairy tales, wizards and cauldrons and wishful thinking. One kind of matter does not become another, everyone knows that. It's practically the first rule of the real world.
And yet it's happening. Quietly. Everywhere. All the time. Right now, as you sit there. In your bones. In the very marrow of them. In the breath you took a moment ago. Particles are changing from one kind into a completely different kind. The exact thing the alchemists broke their hearts over, the thing we all agreed was flatly impossible, is going on this very second somewhere inside your own thumb.
Hang on. The one thing they couldn't do. The impossible thing, the thing every sensible person laughed off for hundreds of years, is just happening? In me? Right now, while I'm sitting here talking to you. Am I transmuting? Is that a thing that's actually occurring? Should I sit down for this, or is it already too late? Have I started?
You can stay exactly where you are. You're in no danger whatsoever. But yes, genuinely, physically, honestly, yes. There is a force in nature whose entire job, its whole reason for existing, is transformation. It reaches into a particle and it changes what that particle is. Not where it's headed, not how fast it's moving. What it fundamentally, deep down, is. One kind of thing turned into another.
Okay, but hold on. A force that changes what something is. That's not what forces do. A force pushes. A force pulls. A force holds things together or shoves them apart. That's the entire job description. That's the whole trade. And you're describing something that doesn't shove me and doesn't grab me. It just reaches in and rewrites me. That's not a force. That's a spell.
That is very nearly the right instinct, and I want you to sit in that discomfort for a second before we take another step, because it really is the odd one out. 3 of the 4 great forces of nature move things and hold things. That's their whole business. This 4th one transmutes them. It's the closest thing the universe has to a genuine magician. And the maddening part is, it's been hiding in plain sight the entire time, right under everybody's nose.
But it doesn't shove, and it doesn't hold, so how does it get anything done at all? What does changing what a thing is even look like from the outside?
That's the eerie part. From the outside, it can look like nothing happened at all. A particle sitting there, and then, with no push, no pull, no spark you could point at, it's quietly a different particle. Was one thing, is now another. That's the whole strange signature of it.
The entire time. So this isn't some exotic bit of business that only happens in the crushing heart of a distant star, or deep inside a machine the size of a small town that we had to build in order to go hunting for it.
It's happening in the bricks of the wall behind you. It's happening in the rocks under the garden. It is, quite literally, the reason the sun came up this morning, and we are going to get there, and I promise you it's better than you're imagining. But first I have to make you believe the magician is real, because absolutely everything tonight hangs off this one strange force.
All right, fair warning taken. I walked in here thinking I knew what a force was. I had the 4 of them lined up in a tidy little row in my head, and you've knocked one clean off the shelf in under a minute. So convince me, what is this thing?
It's called the weak force. And that name, I want you to hold on to it and to remember how it sounds right now, because by the end of the hour, you're going to find it almost offensively unfair. It's one of the 4 fundamental forces, the great movers and shapers of everything that exists, and it is, without any real competition, the strangest member of the set. So let me stand it right next to the other three, shoulder to shoulder, so you can see exactly where it refuses to fit.
Please, line them all up for me. I want to see the odd one out with my own eyes.
Take them in a single breath. The strong force, the one we spent all of last week on, grips the quarks inside a proton and never ever lets go. That's binding. Electromagnetism binds too. It's what holds the electrons swarming around an atom, and on top of that, it pushes and pulls. Like charges shoving each other apart, opposite ones dragging together. And gravity pulls, quietly, patiently, endlessly. The whole cosmos leaning in on itself, every scrap of matter tugging at every other. Three forces: push, pull, bind.
Right. Push, pull, bind. That's forces. That's the entire family, as far as I ever knew. Different versions of the same basic idea, which is things reaching across a gap to affect other things.
Now here's what all three have in common, and it's so obvious that nobody ever bothers to say it out loud, which is exactly why it's so easy to miss. Not one of them changes what a particle is. Shove a proton clean across the room with electromagnetism, crush it under gravity, chain it up tight with the strong force, do all three at once, and at the end of every bit of it, it is still unmistakably a proton. Every force you have ever met in your life rearranges things. Not one of them transforms things. A proton goes in, a proton comes out, always, without a single exception.
And now you're going to tell me the weak force is the exception, the one that doesn't play by that rule.
It's the lone exception in all of nature. The single force whose entire purpose is to change what a particle is. It reaches inside, and it changes the particle's flavor.
It's flavor? Oh, we're back to physicists naming things again, aren't we? Last week it was color that has nothing whatsoever to do with color. Now it's flavor. Let me guess, nothing actually tastes of anything, does it? There's no strawberry quark hiding in there somewhere.
Nothing tastes of anything. I give you my solemn word. It's the very same bad habit. We needed a word for a thing, and rather than invent a good one, we just reached up and grabbed one off the kitchen shelf. Flavor simply means the kind of a particle, its identity. The label that says, this one here is an up quark, that one over there is a down quark. This is an electron, and that's one of its heavier, rarer cousins. Flavor is nothing more than which sort of thing a particle happens to be.
So, flavor is the particle's name badge, the little sticker on its chest that reads, "Hello, my name is down quark."
That's a genuinely lovely way to hold it, and I'm going to steal it from you. And here's the whole point. Every other force in nature reads that badge and respects it. It might push the particle around the room, might drag it here or there, but it leaves the name exactly where it found it. The weak force is the one and only force that walks up to a particle and swaps the badge. Peels off down quark, slaps on up quark. Same slot in the world, completely different identity. And it is the only thing in the entire universe that can do it.
Okay, that one genuinely stops me in my tracks. Every other force in creation treats what a thing fundamentally is as sacred, off-limits, untouchable. And this one just strolls in and edits it, like it's fixing a typo.
Edits it. That's the verb, precisely. The others are all about position and motion and holding things together. This one, and this one alone, is about identity. It's the universe's one and only shapeshifter. And here's the thing. Once you learn to see it that way, some deeply familiar corners of the world suddenly start to make a rather alarming amount of sense.
Then show me one, because right now this is a beautiful, sweeping, abstract claim. A force that changes identity. And my whole instinct is to want to catch it red-handed. In the act, somewhere real that I can actually point at. So where? Where does this thing actually happen?
Then let's go to the most ordinary place it happens of all, something you've heard the name of your entire life without ever once being told what it truly was. Underneath. Radioactivity. One particular flavor of it. Some atomic nuclei are not quite stable. They're carrying a little too much of something, sitting just slightly wrong in themselves, and on their own private, unpredictable schedule, with no warning at all, one of them will abruptly spit out an electron, fling it clean out into the world. And in that same act, it becomes a different element.
A different element, as in, the actual entry on the periodic table changes? The atom was one substance a moment ago, and now, just like that, it's the next one along the row.
The very next one up the table. It was one element, it fired out an electron, and now it is genuinely, chemically, measurably, a different element than it was a heartbeat before. That's what we call beta decay, and people have known about it and named it for a very long time. Long, long before anyone had the faintest idea what was actually going on beneath it. From the outside, all you ever see is an atom cough out an electron and quietly turn into its neighbor on the chart.
And it happens entirely on its own. Nobody has to do anything to it. No heat, no hammer, no spark.
Entirely on its own, on a schedule only it knows. You can't hurry it, you can't slow it, you can't talk it out of it. It sits there looking utterly ordinary for who knows how long, and then, with no warning and no outside cause at all, it simply transforms. The trigger is buried right down where the weak force lives.
And that, right there, all on its own, is already the alchemist's dream, isn't it? One element becoming another, no cauldron required. But you keep leaning on that one word, underneath. What's underneath? What's actually moving down there?
Here's underneath. And this is where all of last week finally pays off, so I want you to reach back for it. The neutron, the neutral one, sitting there in the nucleus, remember what it's actually made of.
3 quarks. You drummed it into me until I could recite it in my sleep. A neutron is 2 down quarks and 1 up quark, and a proton is the same idea flipped the other way round, 2 ups and a single down.
Hold both of those recipes right there, one in each hand. Now watch. Watch what the weak force does, right at the very bottom of beta decay, underneath everything else. Inside that neutron, it reaches in and it takes hold of one single down quark. And it turns it into an up quark. That's the whole move. That's the entire trick, start to finish. 1 down becomes 1 up.
1 quark. It changes exactly 1 quark, and oh, hang on, I can see where this is going. If a neutron is 2 downs and an up, and you go in and flip one of those downs into an up…
Go on, say it. You've already got it.
Then now it's 2 ups and a down, which is… wait, that's the proton recipe. That's a proton. The neutron just turned into a proton, just by changing one single quark buried down inside it.
That is the whole thing, top to bottom. 1 down quark flips into an up quark, and the particle it's living inside stops being a neutron and starts, in that very instant, being a proton. And a nucleus with 1 more proton in it is a different element. The atom has climbed exactly 1 rung up the periodic table, not by gaining some grand new piece, not through any collision or cataclysm, but because a single quark, deep down inside it, quietly and privately changed its kind.
So the real transmutation, the genuine one, the alchemist's actual dream, it isn't the atom at all. It isn't even the neutron. It's 1 quark. 1 tiny quark deciding to be a different tiny quark, and then everything stacked on top of it reshuffling itself to keep up.
That's the heart of the whole thing, and you've put your finger right on it. Alchemy turned out to be completely real. and it turned out to be far, far smaller than any alchemist ever dreamed. Not lead into gold in a bubbling pot, a down quark into an up quark, in a flicker too fast to picture, carried out by a force whose entire and only purpose is exactly this.
And this is going on all the time, not once in a blue moon, constantly.
Constantly, all around you, in those rocks, in the bricks of the wall, in a soft, ceaseless drizzle of it passing through the whole planet, every moment of every single day. Which is why, right at the start, I asked whether you ought to sit down. Because a little of it is happening inside you too.
Inside me. So I really am, in some small, literal way, an alchemist. Or at least the scene of one.
In the most literal and least poetic sense imaginable, yes. There's a wizard at work in your thumb, and it never once asked your permission. Congratulations.
I'm going to need a long, quiet moment with that at some point. But wait, hold on. You said the neutron spits out an electron. Where does the electron even come from? Because a moment ago the neutron was 3 quarks and nothing else. There was no electron tucked away in there. You can't fling out of a thing something that was never inside it to begin with.
Now that is precisely the right question, and asking it opens the next door for us. You're completely right. There was no electron sitting folded up inside the neutron. It's made fresh, brand new, in the very instant of the change, purely to balance the books. When that down quark turns into an up quark, the accounts have to stay square. Electric charge and 1 or 2 other quantities nature guards with a fierce, jealous care. And to keep them square, out comes a freshly minted electron. And that's the electron you see flung clear of the atom.
Okay, made on the spot, conjured up just to keep the ledger balanced. I can actually live with that. Charge goes in, charge comes out, the books stay even, everybody's happy.
Except that when people first sat down and measured this properly, carefully, the ledger did not come out even. And that one small, stubborn discrepancy turned into one of the very finest detective stories in all of physics.
Uneven how? What was missing? What didn't add up?
Energy. When a neutron turns into a proton and throws out an electron, you can add up all the energy going in and add up all the energy coming out. The proton, the electron, every last scrap of it. And the two totals ought to match, down to the last decimal. It's the deepest, most unbreakable rule in the whole book. Energy in equals energy out, always, everywhere, no exceptions ever granted. But the electron kept turning up short.
Short by the same amount each time, presumably. A fixed leak you could at least account for.
That's the maddening part. No, not the same amount at all. It came out carrying a whole smeared-out range of different energies. Sometimes a bit more, sometimes a great deal less, and only very rarely the sharp, single, fixed number the bookkeeping flatly demanded. A smear where there should have been a clean, precise line.
Smeared. So it's not that some fixed chunk of energy went missing every single time, which at least you could hunt for, you'd know what you were looking for. It's that the amount that vanished was different on every single go. Random, slippery, untrackable.
Different every time, and trailing off in a shape that made no earthly sense. And this was a real, cold sweat crisis, because when you looked hard at it, there were only 2 ways out, and both of them were genuinely dreadful. Either energy itself, the single most sacred, most load-bearing law in all of physics, was simply not being conserved in these tiny events, or something, some unseen thing, was quietly leaving the scene of the crime, slipping out the back, carrying off the missing share in a different amount every time.
And giving up on the conservation of energy, that's not a small concession, is it? That's not, oops, let me tweak a number and we'll move on. That's pulling up the floorboards of the entire building. Everything stands on that.
Everything stands on it. And some very serious, very sober people were genuinely prepared. to consider tearing it up. That's how bad it looked from the inside. And then Paulie made a bet. A daring one. A slightly desperate one, if we're honest about it. And it's one of my absolute favorite moments in the whole of science. He said, in effect, no, absolutely not. We do not give up energy. Not today, not for this.
So what was the bet? If he wouldn't break the sacred law, what did he do instead?
Instead, he said there must be another particle. A tiny one nobody had ever seen, slipping quietly out alongside the electron, carrying off exactly the energy that keeps going missing, and, crucially, carrying a different amount each time, which is precisely why the electron's energy comes out smeared instead of sharp. He solved the whole crisis in a single stroke by inventing a ghost.
So rather than break the law, he just conjured up a brand new particle to save it. Out of thin air on paper, purely to make the numbers add back up.
He did exactly that. And here's the deeply human part, the part I love most. This particle he was proposing, for it to actually fit the problem, to slip away completely unnoticed like that, it had to be almost nothing at all. No electric charge whatsoever, barely any mass if it had any mass at all. And it had to feel almost none of the forces, so faint, so shy, so untouchable that it could pass straight through the entire body of the Earth without so much as brushing against a single thing. And Pauli understood exactly what that meant.
What did it mean?
It meant he had dreamed up a particle that, by its own deepest nature, might never, ever be caught. Not with any instrument, not by anyone, not possibly in principle. He'd invented something he suspected was, forever, undetectable.
Which, for a working scientist, is a genuinely mortifying thing to have to stand up and announce, isn't it? Good news, everyone! I've solved the problem. The bad news is that the solution is a ghost, and you will never, ever be able to find it. But you're very welcome.
He felt precisely that mortification, right down to the bone. There's this wonderful, almost sheepish sense of him, half apologizing for the whole affair. Something very close to, I have done a terrible thing. I have invented a particle that cannot be detected. Because a physicist is really not supposed to do that. You are not supposed to conjure up things that nobody can ever, even in principle, catch. It felt to him almost like cheating.
And let me guess how this one ends. The ghost was real.
The ghost was completely real. We call it the neutrino, which means, rather sweetly, the little neutral one. And when that down quark to up quark flip fires off, out comes the electron, yes, and out slips one of these little ghosts as well, carrying the missing energy quietly off into the dark. Pauli's desperate patch, his apologetic little fudge to save the books, turned out to be a genuine, permanent inhabitant of the universe. He had rescued the most sacred law in physics, and he'd been completely right to trust it.
So, has anyone ever actually caught one? Or is Pauli's fear just true, that they slip past everything forever?
Once in a very great while, one does bump into something and leave a faint mark. So, no, not quite forever. They aren't the perfect ghosts he feared. But how you ever catch a thing that ignores the whole Earth is a story worth a night all of its own. And I'm saving it. For now, real out there and barely touching.
So, beta decay, told properly, the whole way through, isn't just a neutron spits out an electron. It's the full chain. A down quark becomes an up quark, and so the neutron becomes a proton. And two things fly out of the wreckage, the electron and this shy little ghost carrying off the balance.
That's the full, honest picture. And you assembled it yourself, one piece at a time. A down turns into an up, a neutron becomes a proton. Out goes an electron, and out goes the ghost. Strictly speaking, it's the mirror version, the anti-neutrino, but let's not get too precious about that particular detail tonight. The thing to hold on to is that second character, the shy one, the one taking the missing energy with it as it goes.
And exactly how shy are we talking here? You keep saying it could pass through the whole Earth. Give me the real, full scale of this thing's shyness, because I don't think I've quite got it yet.
All right, brace yourself properly for this one, because it's genuinely uncomfortable to hold in your head. Right now, as you sit there, doing nothing, just listening to me talk, trillions of these neutrinos are streaming through your body, through your eyes, through your chest, your heart, the small bones of your hands, through the chair, the floor, the bedrock, the whole planet turning silently underneath you. Every single second, trillions of them.
Through my actual eyes. Right now, as we speak? Trillions? That many?
This second. And the second after that, and the one after that, without a single pause, for the whole of your life. A steady, silent, endless sleet of them, pouring straight through you and out the other side, and you feel absolutely nothing. Not a tingle, not a flicker, not the faintest whisper of a sensation. Most of them come flooding out of the sun, and they treat you, and the entire Earth right along with you, as though you simply, flatly, weren't there at all.
That is… Okay, no, that's just rude, honestly. I'm right here. I'm a whole entire person. Trillions of things are passing through me every second, and not a single one of them has the basic common courtesy to so much as tap me on the shoulder on the way past.
Not one. Not ever. And it isn't personal, I promise. It's that the neutrino feels only the weak force. Not electromagnetism. Not the strong force. Only this one strange, feeble, hopelessly short-reaching force, and nothing else. And because the weak force is the single, solitary way a neutrino can ever touch anything at all, and because that force barely reaches across any distance whatsoever, the neutrino barely touches anything. To a neutrino, you are very nearly pure empty space. The Earth is very nearly pure empty space. It sails clean through the whole lot without noticing.
So it's a ghost, not because it's magic, not because it's supernatural, but because the one hand it has to touch the world with is this single, tiny, stubby, hopelessly short little hand. It's reaching out for everything, and its arm just isn't long enough to land on anything.
That's it, precisely. And I want you to hold on to that image, of the weak force barely being able to reach, because it's about to swell up and become the whole mystery of the second half of tonight. But before we go there, I don't want to rush past what we've actually just done, because it's a great deal bigger than it might sound.
Go on then, land it for me. What have we actually just done?
We've found a force that reaches in and changes one kind of quark into another, and we've watched it turn one whole element into the next one up the table. And you might, quite reasonably, still be filing all of this away under fascinating but obscure. Radioactive rocks, the bricks in the wall, a dusty little back corner of nature that never really touches your life. So let me take that comfortable filing away from you right now. Step outside on any clear day and tip your head back and look up. The weak force is the reason the sun is shining.
The sun. The actual sun. The one hanging up there keeping every single living thing on Earth alive. That runs on this, on the same shy little force that's quietly haunting my garden rocks.
It couldn't so much as get started without it. Let me walk you right in, because this part is genuinely gorgeous. The sun shines by fusion, deep down in its core, under a crush and a heat that you honestly cannot picture no matter how hard you try. It takes the very lightest bits of matter and presses them together into slightly heavier ones, and that pressing together releases the flood of energy that eventually becomes sunlight. And right at the bottom of it all, it's building up from hydrogen, from single, lone protons. The simplest thing there is.
Protons fusing together, two of them coming together to start building something bigger and heavier. All right, I'm with you so far. That sounds reasonable enough.
But there's a snag, right there at the doorway, right at the very first step. Two protons cannot simply stick together and stay stuck. A pair of protons, left to themselves, won't hold. They won't stay married. So for the sun to get anywhere at all, at that first step of the whole long chain, one of those two protons has to turn into a neutron. Because a proton and a neutron, those two can hold together. And only then can the building actually begin.
Wait, a proton has to become a neutron? But that's the exact thing we just did, only running backwards. We flipped a down quark into an up to turn a neutron into a proton. So to go the other way, back the way we came, you'd have to…
You turn an up quark into a down quark. The very same magician, working the very same trick, just in the opposite direction. Inside one of those two protons, the weak force reaches in and flips an up quark into a down, and two ups and a down quietly becomes two downs and an up, and a proton has become a neutron. And only now, only after that one flip, can the sun take its first real step. That single flip is the doorway to everything, and only the weak force, nothing else in all of nature, can open it.
So the entire sun, all that light, all that warmth, every green growing thing that has ever lived downstream of it, the whole colossal business is sitting there waiting on this one tiny, shy, feeble little force to flip a single quark and unlock the very first step.
The whole cascade hangs on it, every last bit of it. And here's the part that ought to raise the hair on your arms. The weak force is so feeble, and that first flip so deeply reluctant to happen, that any two given protons down in the sun's core will jostle and shove against each other for an almost unthinkable stretch of time before, once in a very great while, the weak force finally works the change on one of them.
An unthinkable stretch of time for one single flip? That sounds impossibly slow for the very thing lighting up the entire sky.
Impossibly slow for any one pair. But the sun is not one pair. It's a crowd of protons past all counting, all jostling at once. And in a crowd that vast, even a flip that almost never happens is happening somewhere, always. Rare for the one, ceaseless for the whole. That's how a gate that hardly ever opens still pours out a river of light.
Reluctant, so it's a bottleneck, a gate that's almost always shut, that only creaks open once in a very long while.
A gate that's almost always shut, and that turns out to be the greatest mercy imaginable, because that very reluctance, that shyness, is exactly why the sun burns as slowly as it does. Slowly enough to keep shining, steadily, for ages upon ages upon ages, instead of catching all at once and going up in a single blinding flash.
Oh, so the feebleness isn't a flaw at all. I had it completely backwards. The very weakness of the weak force is the whole reason the sun is a steady, patient hearth, and not one enormous, instantaneous bang.
If that force were any stronger, even a little, the sun would have burned straight through itself and gone dark long, long before there was ever anyone standing here to feel the warmth of it. Its shyness is a kind of quiet, world-sized gift, and there's a lovely thing that clicks into place right here, reaching back to something from earlier in this whole grand story. You'll remember that the sun shines by turning a little of its own weight into light, a sliver of its own mass cashed out and paid to us as sunshine.
The most consequential diet in the history of everything. I remember it well, the sun very slowly getting lighter day by day, and quietly handing us the difference as daylight.
That's the one. That's Einstein's business. Mass and energy turning out to be the very same thing, wearing two different coats. So if mass becoming light is the fire itself, then the weak force is the thing that strikes the match. It's what opens that first step, the one single step that nothing else in all of creation can open. Without it, all that vast reservoir of fuel just sits there, cold and silent and useless forever. The second feeblest force in nature turns out to be the gatekeeper of sunlight, and, through the sunlight, of every living thing it has ever grown.
So the same force that's quietly haunting the rocks in my garden is also the sole reason there's a warm sky worth looking up at in the first place. That is an awful lot of range and responsibility for something the world decided to go ahead and call weak.
And now you're finally ready for the part where that name starts to feel like a genuine, actionable insult. Because why on earth is it called weak? What is actually weak about a force that reaches in, transmutes matter, and lights every star in the sky?
Yes, this is the bit I've been waiting for. It changes identity. It lights the sun. It's absolutely everywhere, doing absolutely everything. So where does weak even come from? What did it ever do to earn a name like that?
To answer that properly, I have to carry you back to how a force reaches across a gap at all. The whole picture from a couple of weeks ago. A force isn't spooky action leaping magically across empty space. It's carried. Two particles feel each other's presence by tossing a messenger back and forth between them, over and over, like a game of catch that simply never stops.
The game of catch, right. Electromagnetism is two charges endlessly throwing photons at each other. The messenger of electromagnetism is the photon, which is the very same thing as a particle of light itself.
Exactly, precisely that. And now here is the crucial, load-bearing fact about the photon. It has no mass. None at all. Nothing. And a massless messenger can travel forever. There is nothing to slow it down, nothing to drag on it, nothing to make it run out of road and fall short. So it can carry the force across a room, across a whole planet, across the entire width of the universe if you only give it the time. That is exactly why electromagnetism and light itself reach as far as they do. The messenger has no weight, and so its reach has no limit.
Massless messenger, endless reach. So the range of a force, how far it can actually touch, depends entirely on its messenger. And I am suddenly getting the very strong feeling that the weak force has a rather different sort of messenger tucked away in its pocket.
The opposite kind entirely. The exact opposite extreme. The weak force has its own messengers. We call them the W and the Z particles, and where the photon has no mass at all, these two are right out at the far end of the scale. They are heavy, enormously, almost absurdly heavy. Among the very heaviest particles we have ever found anywhere, far, far heavier than a proton, heavier than the whole little huddle of quarks they reach in to act upon. The messenger of the weak force is a giant.
Heavier than the very things it acts on. That still sounds backwards to me. Where does all that weight even come from for something that lives for barely an instant?
Ah, now you're leaning on the exact door I mean to keep shut a while longer. Where that weight comes from is one of the great questions, with its own night still ahead of it. For tonight, take the heaviness as a brute fact and watch what it does to the force's reach. Because that is where the whole word weak has been hiding.
Now, that is a genuinely strange picture, all on its own, before we even get to the range business. The messenger, the thing carrying the message, is heavier than the particles it's carrying the message between. That's like posting a letter, and the letter turns up strapped to the back of something bigger than the house it's addressed to.
Much, much bigger than the house. And that heaviness carries one devastating consequence along with it. And that consequence is the whole and entire answer to your question. A heavy messenger can barely travel at all. It can only flit out for the tiniest sliver of an instant, the shortest little hop imaginable, before it has to vanish again. And so the weak force can only reach across the most minuscule distance, less than the width of a single proton, and then it simply switches off. It has almost no reach whatsoever.
So, wait, let me make absolutely sure I've got this straight, because I think it matters. The weak force isn't weak because it's gentle, because it's some soft little push. Up close, right up in there, within its reach, is it actually feeble at all?
That's the twist, and it's the single most important thing to carry home with you tonight. Up close, right up against another particle, well within that tiny whisker of range, the weak force is not feeble in the slightest. It's forceful, it's fierce, it gets real heavy work done, it flips quarks, it lights entire suns. It only seems weak from where we're standing because it can hardly reach anything at all. The heavy messenger simply cannot carry the message any distance. So almost everywhere, almost always, from our point of view, the force is just plain absent, switched off, silent, throttled by the sheer dead weight of its own messenger.
So weak is basically a slander, a libel. The honest name, the fair name, would be something more like the incredibly short-armed force. It's not that it can't throw a punch, it's that its arms are barely long enough to reach far enough to land one on you.
The short-armed force. Honestly, I wish that had been the name. It's so much more truthful. A tremendous, devastating punch mounted on an arm barely long enough to reach past its own chest. Set the two extremes side by side, and you can see the whole story at a glance. The photon, weightless, reaching out forever. So electromagnetism is simply everywhere you look, in everything you touch. And the W and Z, massive, reaching almost nowhere, so the weak force seems to barely exist at all, even while, in its own tiny private domain, it's quietly doing the most extraordinary job of the entire cast. Heavy messenger, short reach, apparent weakness. That is the whole of why it's called the thing it's called.
And that snaps into place with something you dangled in front of me ages ago and then never resolved. You said a massless messenger reaches clean across the universe, and then you asked, well, what would a heavy one do? And then you just wandered off and left it. This is the answer, isn't it? A heavy one barely reaches at all.
This is the answer you were promised. The entire character of a force, its whole personality, is written into its messenger. Give the messenger no mass, and you get a force that spans the whole cosmos. Give it a great, crushing weight, and you get a force chained to a spot smaller than a single atom. Same basic machinery underneath, a traded messenger thrown back and forth, and yet the mere weight of that one messenger decides absolutely everything about how far the force can ever hope to touch.
Okay, but you can't just drop "they're among the heaviest particles we know of" and then stroll calmly past it, because now I need it. Why are they so heavy? Where does a messenger even go to pick up that kind of weight?
That is a magnificent question. Genuinely one of the very deepest questions in all of physics. And I am now going to do something a little bit cruel to you. I'm going to leave it sitting right there, untouched, glowing on the table between us. Where the W and the Z get their enormous mass, where any particle at all gets its mass, when you truly chase it down, is its own extraordinary, season-turning story, and it belongs to a later night in this series, not to this one. For tonight, just hold the plain fact of it. They're heavy. That heaviness is why the force is so short-armed, and that shortness is the whole of the weakness.
Fine, but I'm writing it on the wall in big block letters. Why are they so heavy? You are absolutely not escaping that one, my friend. I'll be waiting.
I wouldn't dream of trying to escape it. But before you go filing the weak force away in your head as, right, understood, next, short-armed, changes flavor, lights the sun, I have to tell you the very last thing about it. And this one is not a footnote. This is the strangest single fact I know about the entire universe. And this shy, feeble, short-armed little force is exactly where that fact lives.
The strangest single fact you know about the entire universe. You have already cleared an extraordinarily high bar tonight, so this had better be good. Go on, hit me with it.
Let me set it up with something so obvious that it sounds almost silly to say out loud. Hold up your right hand and look at it in a mirror. What looks back out at you?
A left hand. Obviously, that's the entire job of a mirror. It swaps left and right. My right hand's reflection is a left hand. Everybody's known that since they were about 3 years old.
Now here is the deep, quiet assumption that every single person in physics carried around with them for centuries without ever once quite saying it out loud. That the universe itself cannot tell the difference. That anything nature is able to do, its mirror image is equally allowed to do. Take any process at all, any experiment, any event, anywhere. Reflect it, flip its left and its right, and what you see in that mirror is something nature is perfectly, equally happy to actually go and do. The real world and its reflection were assumed to be equally real, equally possible, equally at home in reality. Nature was ambidextrous. It had no favorite hand.
And that just feels correct, doesn't it? Deeply, obviously correct. Why on earth would the universe give the faintest care about left versus right? There's nothing special about either one of them. My own left and right are just an accident of which way I happen to be facing this second. Turn me around and they swap. Space itself doesn't have a handedness stamped on it. That's not even physics, that's just common sense.
It's beautiful, and it's sensible, and it feels as solid as bedrock under your boots. Everyone believed it. Every single person. And then the weak force strolled in and broke it clean in half.
Broke it how? How do you even go about breaking something like the mirror image is also allowed? What would that even look like?
By finding a process, a real one, whose mirror image nature simply, flatly refuses to perform. The weak force, it turns out, has a handedness built right into its very bones. It acts on particles of one particular handedness, call it left-handed, and it all but completely ignores the mirror-flipped version. It genuinely, deeply cares which way round the world is.
Okay, hold on, slow right down. Because the handedness of a particle is a brand new thing you just quietly slipped into the conversation. What does that even mean? What does it mean for a particle to be left-handed or right-handed?
Fair. It's a strange idea, so let me hand you a picture for it. Think of it, loosely, as a particle spinning as it flies along, like a thrown ball with a spin put on it. Spin it one way, relative to the direction it's traveling, and you could call that left-handed. Spin it the other way, and that's right-handed. And a mirror flips the one straight into the other, exactly the way it flips your two hands. And here is the shock, the whole shock. The weak force acts, overwhelmingly, lopsidedly, on the left-handed ones. So hold a weak force event up in front of a mirror, and the mirror shows you the right-handed version of it. And nature, out here in the real world, hardly ever does that one at all. The reflection is a thing that essentially never happens.
So if I filmed an actual beta decay and then filmed its mirror image, and I showed you both, you could tell me which one was the real event and which one was the reflection. Just from the physics itself, not by spotting a clock ticking backwards or writing that reads the wrong way round, from the actual bare laws of nature.
That is the earthquake, and you've just stated it perfectly. You could tell, every single time. There is a genuine fact of the matter about which one is real and which one is the mirror. The mirror world, for the weak force, runs on a physics that our world simply does not run on. And that means, sit with this for a second, the universe is not ambidextrous after all. It has a preferred hand. It can tell its left from its right.
No, hang on just a second. The universe has a favorite hand. Since when? Who decided that? On what possible grounds does reality itself get to sit there and prefer left over right? That offends me on a level I genuinely didn't know I had.
I love that it offends you. because it offended absolutely everyone. When this was first discovered, it genuinely stunned the very people who found it. It was one of those results that nobody quite believed, that everyone assumed simply had to be a mistake somewhere, right up until it would not go away, no matter how many times or ways they checked it. Some of the sharpest minds alive had been so completely certain that nature was even-handed that they had never once seriously thought it was worth the trouble to check. And then someone finally did check, and the mirror cracked straight down the middle.
And that's not just some quirk of beta decay then, that's the force itself, everywhere it acts.
Everywhere it acts, every flip, every transformation it performs carries that same handedness baked right in. It isn't a fluke of one experiment, it's the personality of the whole force. Wherever the weak force reaches, it reaches with a left hand. And that, more than anything else it does, is what shattered the old picture of a fair, even-handed universe.
And I want to make sure I'm not overselling this to myself in my own head here. This isn't the weak force has a slight statistical preference, a small lean in one direction. You are telling me that reality itself, right at the deepest level, is genuinely, structurally lopsided.
Genuinely lopsided, at the very deepest level we have ever managed to reach. Of the four forces, three of them are perfectly, scrupulously even-handed. Gravity, electromagnetism, the strong force could not care less whether you've reflected the world or not. Run any of them in a mirror and you would never, ever be able to tell. The weak force is the one place, the single, solitary place in all of nature, where the universe quietly keeps a secret preference, where it tells left from right and then acts on the difference. And nobody knows why it's that hand and not the other one. It just is. That's the honest answer. It simply is.
That is exactly the kind of fact that keeps a person lying awake at night. And not because it's complicated. It isn't. It's brutally simple. It keeps you up precisely because it's so simple and so utterly wrong-sounding. The universe has a handedness, and of all the places for it to live, it lives in the one force whose whole job is to change what things are.
The shapeshifter is also the very same force that broke the mirror. That's the thing to sit with tonight. The same strange, short-armed, feeble little force that transmutes quarks and strikes the match beneath the sun is also the single, solitary crack running through the whole of nature's symmetry. It's as though the one force that dares to rewrite identity also decided, while it was at it, to refuse to respect the one symmetry that every physicist alive was utterly certain the universe would never, ever dream of breaking.
When you line the whole thing up like that, it really is faintly absurd, isn't it? It changes what particles fundamentally are. It starts up the sun. It's so short-armed it seems barely present in the world at all. And on top of every bit of that, it can tell its left hand from its right when nothing else in the entire universe can manage the trick. That is not a force. That is a personality.
It's the family eccentric, and I've grown genuinely, helplessly fond of it over the years. And look what we've actually gone and done tonight, almost without noticing we were doing it. We've finished the map.
The map, all four of the forces.
All four of them, in hand at last, laid out in a row. Gravity, aloof and patient, pulling quietly across the whole width of the universe, still standing a little apart from the rest of the story. Electromagnetism, trading photons back and forth, binding atoms together and carrying every scrap of light there is. The strong force, gripping the quarks with colour and never once letting a single one of them go free. And now, tonight, the weak force, transmuting identity, striking the sun's first match, wielding those two impossibly heavy messengers, and keeping the universe's one lopsided little secret all to itself. Four forces, that's the whole set. That is, quite literally, everything that pushes, pulls, binds or transforms in all of nature.
That honestly feels like an ending, a proper one. 4 forces mapped out, the whole board finally laid flat and out in the open. Is that it? Is that the story?
It certainly feels like an ending. But here's the thing. All night long, one character has kept quietly slipping out the side door every single time our backs were turned. Every time the weak force did its work, every beta decay, every reluctant flip in the deep heart of the sun, it coughed out that one little ghost, the neutrino. And we've been treating it, this whole time, as a bit player, a spear carrier, the shy thing that scoops up the missing energy and then vanishes off into the dark.
The one that's sleeting through my eyeballs by the trillion, even as we sit here having this conversation. Rudely, without so much as asking permission.
That one. That exact one. And here's what I've very deliberately not told you yet. That ghost, no charge, feeling only this one hopelessly short-armed force, sailing clean through you and the whole turning Earth without so much as a nudge, is hiding a secret. Something it does on its long way here to us from the sun that sounds, the first time you hear it, frankly impossible. We've spent this whole season on particles that stay stubbornly what they are. And the neutrino, the single shyest thing in all of nature, the one that barely touches the world at all, does something on that journey that absolutely nobody saw coming. And that took years and a real fight before anyone could bring themselves to believe it.
You're doing the thing again. The pause. You've handed me a cliffhanger, and now you're just going to leave the shyest particle in the entire universe standing there in the doorway, holding its secret while the credits roll.
I am, because it has genuinely earned its own night, and I refuse to cheat it out of one. We've only ever met it in passing all evening. Paoli's desperate patch, the ghost that saved the sacred law, the thing you can't feel pouring through you. Next time, the shyest particle in all of nature stops being a footnote in somebody else's story and walks out to take the whole stage for itself. And I promise you, I really do promise, what it has been quietly hiding this entire time is more than worth the wait.
All right, then I'll sit with it, the way you always make me. A force that plays alchemist deep inside my own thumb, that strikes the match beneath the sun, that's so short-armed it seems to barely be there at all, and that somehow, impossibly, knows its own left hand from its right when nothing else in all of creation does. And sailing straight through the middle of all of it, a little ghost pouring through me right now, this very second, carrying off a secret I'm apparently not allowed to hear until next time. Next time, then, the ghost that barely exists.